Our journey through the proofs began with the simplest approach and was followed by Euclid's classical method from over 2,000 years ago. Now, we leap forward to 1938 to Hoosier Land in South Bend, Indiana, where Ann Condit, a 16-year-old high school student, approached this ancient theorem with fresh eyes. Ann's proof is born in a different era and from a mind outside the traditional scholarly corridors. Yet it challenges and expands our understanding of geometric principles. Let's retain our same ABC triangle, but this time let's mix things up by changing to a 5, 12, 13 triangle with the longer side as the base. Recall in our first two proofs, we drew a segment from point C to create a perpendicular line to the hypotenuse. Ann's first segment also starts at point C and heads towards the hypotenuse, but rather than choosing the perpendicular, Ann's destination is the midpoint of the hypotenuse, point M, and choosing this destination was like Columbus choosing to sail to America. It opened a world of new possibilities that Ann unleashed. Now, where exactly point M resided was a mystery to me until I saw the symmetry at play. We know a right triangle is half a rectangle, which has 4 right angles producing symmetry. The symmetry results in both diagonals being of the same length. If the top right green point is BA, then M's coordinates, being the midpoint from the origin to BA, are B over 2 and A over 2. And like Euclid, N creates squares A and B based on side lengths little a and little b. The magic of this midpoint is that we can draw segments from point M parallel to each axis, dividing squares A and B in half, producing 2 blue rectangles, each with height A over 2, and 2 green rectangles, each with width B over 2. You can think of Columbus setting sail straight west parallel to the equator from point M and also due south from point M. Most of Ann's ideas formulate around squares A and B. So first, we'll consider square B with side length little b. Since Ann's segment from N cut the square in half, each rectangle's area is b squared over 2. Ann's next move is brilliant, as she connects point M to point E, creating triangles CME. The stage is now set to calculate the area. We need a base, and we have 3 bases to choose. Ann chooses CE as the base, which is length B because it's the side of square B. Can you identify the triangle's height? Height is the length of the segment perpendicular to the base, stretching until it reaches the line parallel to the base that intersects point M. The height is the length from C to the midpoint between C and A, and since the entire side length is B, midpoint is B over 2, so height is B over 2, and thus area is 1/2 times B over 2, or B squared, all that divided by 4. We can think of the triangle's area as 1/4 of the entire square's area, or half of the shaded rectangle. This approximation looks reasonable, but we enjoy the satisfaction of knowing it's exact. Now move to the blue square A and rinse and repeat. Create triangle CMG using a similar strategy to CME. Choose side CG as the base, and the height is A over 2. The triangle's area is A squared all over 4, and again, the triangle's area is also 1/4 of the entire square's area. Put these pieces together by summing the areas of both triangles to equal A squared plus B squared all over 4, which is the left side of our famous equation. In the bottom left corner, you can see a smaller picture of both triangles with the original black ABC triangle to see the big picture. And notice that both triangles share the same common side from the origin to point M. And since we know how the story ends, we know we need letter C to make an appearance. So, What if we could prove that the total area of blue plus green also equals c squared all over 4? If we could, we would be stating both the left side and right side equal the same area, and our proof would be complete. To start, let's retrieve our animation from the previous video. Now, follow me on this path where we just assume the base length is c over 2 and the total height is c. We don't need to know the individual heights, just the sum total. If somehow these assumptions actually are true, then the area of triangles blue plus green is 1/2 times c squared times c, or c squared all divided by 4. Now this is not proving anything, of course, but it targets what we're aiming for. That means to hit our target, we must meet 2 goals. One is prove the base is c over 2 for both triangles, and 2, prove the total height is c. We'll shoot for goal 1 first by proving the base is c over 2. Return to the initial triangle and review Ann's midpoint cut. How do you think segment MC compares to MB? They look similar, but is that a coincidence? They are, in fact, equal. Here's how I realize this. Retrieve the rectangle we created earlier. The symmetry is striking, like a pan of brownies cut on the diagonal. All 4 pieces are isosceles triangles, and opposite triangles match, meaning MC and MB are of equal length. Since the hypotenuse length is c, MB is c over 2, so MC is also c over 2, and yes, we achieved goal 1. Now for goal 2, we need the height of each triangle. And to me, this is the most difficult part of all 3 proofs, and I struggled mightily to see it. Now, even though this is a big step, we are set up for success from our previous video. Return to our area blueprint, where we simply define the height as c. Then compare these triangles to the smaller view of our actual triangle setup. Our model shared base points to 3 o'clock left to right. However, in Ann's setup, the base and height are rotated slightly, pointing to about 2 o'clock. Rotate our picture so the shared base points to 3 o'clock, matching the 2 pictures. In Ann's picture, the height is the hypotenuse of the original triangle, which we know is c. There's another right triangle at the bottom, also with side lengths a and b, meaning the hypotenuse is also c. So, with our eagle eyes on, we identify the total sum height of the blue and green triangles is in fact c, achieving goal number 2. And if you're like me, it will take a while to truly see this, but stick with it as the thrill is worth the effort. Substituting into our triangle area formula, the area of sum of green and blue is c squared over 4. And thus, we have created 2 expressions for the sum of the green and blue triangles, a squared plus b squared all over 4 and c squared over 4. And since their areas originate from the same 2 triangles, we can equate their expressions, multiply both sides by 4, and Ann makes history by proving a squared plus b squared equals c squared. However, one minor detail remains. We assume that the segment from M through C intersecting the hypotenuse was perpendicular. Let's button up this missing element. Since the lengths of MC and MB equate, triangle CBM is isosceles, making corresponding angles congruent. Also, angle PCE is congruent to these 2 angles because opposite or vertical angles are congruent. We also know that angle PEC is congruent to CAB because triangles CAB and CEG are congruent. And thus, triangles CAB and CEP each have 2 congruent angles, and since all triangles sum to 180 degrees, the third angle must also be congruent, making BCA and CPE right angles. So segment CP is indeed perpendicular to PE, completing Ann's proof. Not only is this an amazing proof, but Ann was the first and only to use midpoint M as the basis for all her segments. Nice work, Ann. Gee, I wonder what I was thinking about when I was 16. Well, maybe creating one more proof doesn't sound impressive, but let's put this into context. Euclid's proof was more than 2,000 years before Ann's. And not only is that a lot of time, but some of the best minds in math have thought about proving the Pythagorean Theorem. Yet Ann was the first to see this proof. And now you, almost 100 years later, have seen the work and shared the mind of a relatively modern-day genius. And that means you understand something deep and profound that many of the great math minds of the past did not have the pleasure to know. We've completed all three proofs, which means we've finished part one and are ready to go off-road in part two, where I, and now we, are on our own. And for me, being off-road is where the fun math really begins.